solve these problems, oftentimes we use all three. This last one, the Darcy-Weisbach equation, we talked about last time as a way of having one equation that can be used to find the pipe friction head loss. In both laminar flow and turbulent flow. And again, we're solving these pipe flow problems where there's some distribution of velocity across the pipe. It has a diameter d and a cross-sectional average velocity v. And as we'll see, there's three types of problems that are of this sort. The simplest sorts are the type where you're calculating the head loss due to friction, and the most complicated are where we're given information on the pipe and the flow, and we're asked to figure out what size pipe could deliver that flow with that available head loss. These are referred to as type 1, 2, and 3 problems, and we'll do examples of this on each of these next time. One topic from last lecture on the difference between laminar flow and turbulent flow I didn't get to. We talked about the qualitative differences between laminar flow and turbulent flow. Again, of a pipe diameter d. Trying to make two distributions that are similar or nearly identical in the same average velocity, but different in the distribution of velocities from center to the wall. Which one, we mentioned this briefly, but which one is the laminar flow case? The pointy one or the flat one? Who says pointy? Who says flat? Okay, the flat one is the turbulent one, okay? And the pointy one is the laminar. It's actually parabolic. There's an equation you can write for the velocity distribution as a function of the radius from the center. They both have their maximum velocities in the pipe center. But how that maximum velocity corresponds to the average velocity varies for the two cases. For laminar flow, it's exactly 2.0. And as a result, you can write an equation for the velocity at any location from center to the pipe wall in laminar flow, given this fact that the maximum is twice the center and that it's parabolic. And if you go to the FU reference handbook, you can actually see an equation for the velocity distribution in laminar flow. Turbulent flow, that ratio of the maximum to the average is less than 2, and there is an equation for that, given a special name. Called the pipe factor, and that's this is the inverse of what we were showing over there, but it's the average over the maximum. And that's an equation for it. And remember this thing, this F, is something we call the friction factor. It's in our Darcy-Weisbach equation. And we're going to use this very well-known diagram called the Moody diagram to find the value for F. That's the subject for today, finding these friction factors. Something I don't see mentioned in this textbook, but I know that it's something that might come up, is the possibility of pipes that aren't circular. You can define this thing called the hydraulic radius. Which is the area of the pipe over the perimeter of the pipe, or a circular pipe that's D over 4, and for non-circular pipes, a version of the Darcy-Weisbach equation that will get used. And you can simply, if you substitute R sub H into our Darcy-Weisbach equation here, you can see it as FL over so we're going to have two cases, circular and one that works for any pipe shape, but both of them require the Moody diagram. Oh yeah, now I know where. For those of you in software design, an essential skill for presentation 3. Okay, presentation 3 is when you have to actually go to the board and use it, is to learn how to write on the board with chalk and not make it squeak. Okay, because you will just have your audience completely distracted if your writing on the board with chalk is squeaky. So my recommendation is to practice a little bit of writing on the board. It's also surprisingly difficult to make what you write horizontal. I often angle it up, and I'd say it takes some practice. So what we're back to this, we're saying is this Moody diagram gives us the friction factor as a function two-dimensionless numbers. Reynolds and relative roughness, where we said last time that you'll either see it as a small e or an epsilon over the pipe diameter is one non-dimensional number, and the other is this Reynolds number. What we had said is that there's a value for the laminar flow case that's very simple. It's just 64 over the Reynolds number. In a turbulent flow case, it's more complicated. And as we'll see, it depends upon a third dimensionless number, at least in the way that we analyze it. Depends on this this other length scale. This is like I'm trying to make a little delta here, delta sub V, which is the viscous sublayer height. And we'll get to that in a minute. I had wanted to show the Moody diagram. Let's show the Moody diagram. Yeah. And I'm looking at it here on the screen, and you're, yeah, okay, I will come. Yeah, why don't you just turn it there, Swing, and those of us in the class can see it on the, there. But I think I can just do it from here. So what we have then is a diagram that shows the two dimensionless numbers on the x-axis. That's the Reynolds number from low to high, from left to right. And you see a bunch of lines. Each of those lines represents a different value for the relative roughness. So the y-axis that's on the right is the relative roughness scale. And so very rough pipes are at the top. The lines at the top are the high relative roughness, and the lines at the bottom are low relative roughness. And what you would do is get on the appropriate line for the whatever relative roughness you have, and then find the point on the diagram that is the intersection of the Reynolds number you have and the relative roughness that you have, and then from there read over to the left to give the friction factor for that particular case. So let's just try one. I'm going to say the relative roughness was 0.01, okay? And the Reynolds number is 10 to the 6th. 10 to the 6th. 0.01 and 10 to the 6th. And just gonna write that down. And you on the call, the Zoom call, and you at here, look at the diagram and say we want epsilon over D, and we want the Reynolds number, and we want the friction factor that goes with it. This is from the Moody diagram. We'll just do a couple practice before we go on. What'd you get? It's kind of hard to see. What you'll first discover is that this binding of friction factor is not something that's very precise, because you're reading lines. I will come forward, find 0.01, yes, 10 to the 6th, put the pointer right there. Oh, okay. 0.0, where'd it go? Okay. Okay, it would be right there. I'm going to do the same thing. So look at that if you can see that. I'm going to do the same thing on this. Well, here's 10 to the 6th. I'm going up. And it's right there. So we get a friction factor here in the class. And then you read over to the left, and it's a little less than I'm going to say, well, I'll ask somebody to give me their guess first before I put mine.
3.039.
Ha, that's what I got as well. Okay. Now, just to make a point, and so that we don't have to do this, what happens if we raise the Reynolds number by a factor of 10 from there, and then a further factor of 10 from there? What do we see?
Basically nothing.
Yeah, no change, right? No change. And the diagram gives us a hint as to why that might be. It's that dashed line. They call it complete turbulence. If you're on the diagram to the right, or to the above and to the right of that dashed line, you're in the region that this, my diagram, calls complete turbulence. What's it called on?
It's the same
Oh, it's the
diagram.
same diagram. But in the textbook, it's a different version in the textbook. And I've also seen it called fully rough. And that's the region where the friction factors don't depend on the Reynolds number anymore. They only depend on the relative roughness. Okay, so that's one possibility. for the turbulent case is that it only depends on the relative roughness. There are other cases where it depends both on the Reynolds number and the relative roughness, and we'll get to that. But what I said is that in trying to figure out how this is working, what we need to look at is another ratio. We're trying to figure out the different regions within the Moody diagram. What we want is this ratio and I'm going to start off with an equation for this length scale, and then go from there to show a picture of how this viscous sublayer thickness is operating inside the pipe. First, let's get an equation for it. Now, there's no you can think of this as the distance from kind of hard in talking about this not to think of the image. And the image you'd have is to say that right along the edge of the pipe, where the velocities are low and the wall of the pipe is near, there is going to be a region where the flow is laminar. That distance from the edge of the pipe we refer to as the thickness of a viscous sublayer. So the inside of the pipe has this viscous layer. How would we calculate it? Well, it's roughly equal to depends on this thing called the friction velocity, generally referred to as U star. Just putting in the dimensions here, see that you get a length. That's the kinematic viscosity in the numerator. The shear velocity or friction velocity is equal to the shear stress at the wall divided by the density, and an equation that makes more sense to us is to relate it to the cross-sectional average velocity and the friction factor, unfortunately. So we don't really know what the friction factor is or how to calculate it, but it has something to do with the relationship between this characteristic velocity for characterizing the friction and the cross-sectional average velocity. And I would say that it's sufficient to think of the viscous sublayer thickness as a small distance from the edge of the pipe, away from the pipe where the viscosity is important, where the flow is laminar. Exactly what that number is not so important, because we're thinking more qualitatively at this point than quantitatively. So think of that thin little distance called the viscous sublayer. And now we so we're zooming in on a pipe, and on the pipe has some roughness. Has some bumps on it that have a height epsilon. And what we can have in our two cases is sort of two possibilities. Okay, so we can think of these two cases as smooth or fully rough. And I'm going to make some more pictures based upon these two cases. Like we said, this is also called complete turbulence. All right, so let's do the fully rough one first, because I think it's easier to imagine if the viscous sublayer thickness is small. So here's our epsilon, and then this thickness is our viscous sublayer. What we have in that case is only a very small region where that's just above the roughness elements, where there's any effect of viscosity. And for the most part, there is turbulent flow everywhere else. In that case, you can see that that effect of the roughness is only modified a very little bit by the viscous sublayer thickness. And in this case, the friction factor is only a function of the ratio of the roughness element to the pipe diameter. That's what we call fully rough. Okay, and then how about the other possibility? Smooth pipe, but it's turbulent flow in that is, it's a Reynolds number greater than 4,000, but a smooth pipe. So in this case, we might have a viscous sublayer thickness of that, and a roughness height of that. So in that case, the roughness elements and then out, so we've got maybe laminar flow here and turbulent flow there, but what's going on in the pipe doesn't get affected so much by what the roughness element height is, because it's contained within the viscous sublayer. And in that case, F is a function of only the Reynolds number. Because whether you make this height or half that height or a tenth of that height doesn't really change anything, because it's contained within the viscous sublayer. So that's the two limiting cases. And then the transition is when both things matter, both the Reynolds number and the relative roughness matter, and that's where the two length scales are approximately equal to one another. So then you've got a roughness or a sublayer thickness that's something like that. And you can see that in this case, changing the height of that roughness element would have a significant difference on what's happening near the wall, as would changing the thickness of the viscous sublayer. And so in that region, we've got both factors, the roughness factor and the Reynolds number factor of some importance. All right, so to sum up, got three possibilities. And the term hydraulically smooth is used because it means it's not so much that the pipe is smooth, but for the purposes of this particular case, it's smooth enough that the effect of changing the roughness isn't important. So like we said, that it's only a function of Reynolds number. Here it's only a function of relative roughness. Here it's a function of both. And these various functions have been determined by a bunch of experiments. The equations you find in the textbook are empirical equations. And generally, what we do, at least in problems we work here, is we use the Moody diagram because the Moody diagram has all three of these cases in addition to the laminar flow case built into it. So I'm going to go back to the Moody diagram. Okay. And so now, do you see on the diagram, we can think there's these three cases, and then there's also the fourth case, which is the laminar flow case. And let's find the f as a function of whatever for those four cases. All right, do we see the laminar flow case? Yeah, it should be down a straight line on the far left of the diagram. And it's got a label on it that says laminar flow 64 over Reynolds number, okay? And then working backwards, the fully rough, right? The only thing that matters is the relative roughness, meaning that the lines that you see on the Moody diagram are going to be horizontal. That is, moving to the right or left, that is changing the Reynolds number, will not change the friction factor. That's called fully rough. Hydraulically smooth, I think the way to see this is say that you're at a Reynolds number of 10 to the 5th, and it's a rough pipe. It's a rough pipe, a relative roughness of 0.02. Okay, so that would give us a friction factor. So let's just, in fact, yeah, this is a good thing to do because I've seen students get confused in exactly this circumstance. So let's do this. Let's say, all right, so give me a relative, or maybe we should see if we can go, yeah, that's good. Okay, so if I said, what's it called here? Complete turbulence. so give me a value for the relative roughness with a Reynolds number of 10 to the 5th that's in the region of complete turbulence.
Were you looking for friction factor or the relative?
No, all I want is, if I told you the Reynolds number was 10 to the 5th, and I told you it was complete turbulence, there's not a single answer here. Give me a value of the relative roughness that's in that region. The people on the Zoom call could.
0.01.
0.01 is the suggestion from Nathan. Let's check that out. 0.01. Okay, so let's look at this combination and confirm that, see the dashed line? Is it up and to the right of the dashed line? Yes? No? Yes, it is. Okay, and then the friction factor that you'd get for that? Roughly? 0.39. Okay. The same found. Now let's say that we made it, I don't know, do they have a 0.003? Let's make it about 1/3 as rough. I don't see which line, do we have a line for that?
No.
0.002.
Yeah. no.
Okay, let's do 0.002. Same Reynolds number. And look to see what's the region.
Still complete turbulence.
Still completely turbulent. And get an F for that.
Right, 0.002 out of Reynolds number of, oh, that's not.
This combination, we expect it to be somewhat less than that, right? We've made the pipe smoother and we're in the completely rough region.
No,
So we think it,
0.002 at 10 to the
it's
5.
not in the completely rough region?
I
No?
was wrong. Okay.
Oops, we,
It's in transition.
it's in transition, okay. Now we do expect a lower friction factor because we've not changed the Reynolds number, but we've made the pipe smoother. 0.025, okay. Is that, ask questions out there on the Zoom call if you're not getting that.
I don't think we did the first one right. Because 10 to the 5th would leave us in between 0.01 and 0.005 for our relative pipe roughness.
Do we have a 0.01?
Yeah.
0.01, 10 to the 5th.
One is above the dash line, so it's assuming complete turbulence.
Yeah, it might be a little less than 0.039, but it's I might, if I were to do it, I might call it. I mean, it doesn't, you're never gonna get a wrong answer by giving the wrong friction factor to the 3rd decimal place, so. But in looking at that, I might say something like that, 0.037. And is it in fully rough? Yes, it is. It is. And then it crosses over to transition for 0.002. Okay. And now let's do 0.001. I'd say it's still in transition. At that Reynolds number. And I get a friction factor of 10 to the 5th, about 0.025 again, maybe? Oh, sorry. 023, yeah, 023. 023 looks about right to me. Okay, now what would happen if we went to 10 to the minus 4? That's hydraulically smooth.
0.018.
And making it smoother than that would make it even. And even if there isn't a 10 to the minus 5th on the figure, is there? Yeah, actually there is. See how all the lines collapse to 1. So that means that the relative roughness is no longer playing any impact on the result, and you get a friction factor of about 0.017. Okay. So that's where we're going to leave it. Now that we're good at using the Moody diagram, we can actually use it to solve problems next time. Where do you have to go after this for dinner?
My apartment.
Oh, okay.
To work on other assignments.
Okay. I thought we finished early like this. Questions? Any other questions?